Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This video is one in a playlist on probability distributions. The playlist is planned to include a three-part series on distributions as a whole, plus individual videos on 9 different types of distributions, as well as several on the properties of distributions. See statisticsfromatoz.com/videos for the latest status of this work. You may find it helpful to view the first 2 videos before viewing this one, but that is not required. As usual in the book and in these videos, we'll start by going quickly through a list of keys to understanding, or KTUs. This is to give you the overall picture of the concept on one page. And then we'll go into detailed explanation of each of the keys. For this video, there are 5 KTUs. The first key to understanding tells us that the exponential distributions can be used to solve problems involving the time interval to events or between events. The second key says exponential distributions can be used when events occur independently and at a constant average rate. The third key to understanding says the exponential is a family of continuous distributions. An individual distribution within the family can be specified by a single parameter, either the mean, mu, or the rate, lambda. The fourth KTU states the probability curve, PDF, of an exponential distribution approaches 1 as x approaches 0, and it approaches 0 as x approaches infinity. KTU number 5. The cumulative probability, CDF, of the distribution can be calculated with the formula as shown. And here on one page are the 5 things that are key to understanding the concept of exponential distribution. You may wish to pause the video at this point and read them all together. Let's now go into more detail on each of the keys to understanding. KTU number 1 says, exponential distributions can be used to solve problems involving the time interval to events or between events. For example, we own a small shop and one new customer arrives on average every 15 minutes. So the mean time interval between customer arrivals is 15 minutes. We would like to close up shop 10 minutes early today. What is the probability that a new customer would arrive after we left, but before our normal closing time? The exponential distribution can help us calculate the probability of a customer arriving in that 10-minute time interval. Similar uses include time to complete a process step and time between equipment failures. The mean time between events is the inverse of the rate at which the events occur. In the example above, a mean time between customer arrivals of 15 minutes corresponds to a rate of 1/15 of a customer in 1 minute. So the mean is equal to 1 divided by the rate, and the rate is equal to 1 divided by the mean. The symbol for mean is the Greek letter mu, and the symbol for rate is the Greek letter lambda. So mu equals 1 over lambda, and lambda equals 1 over mu. Mu and lambda are the inverse of each other. Here's a note on terminology. Expected value, E, is a term used almost synonymously with mean in this context. In our shop closing time example earlier, we started with a known value for the mean interval, 15 minutes, and then we calculated a value for the rate. If we had instead started with a known value for the rate, say 4 customers per hour, we could have then calculated an expected value for the time interval between future customers. That would be 15 minutes. We call it expected because it is a projection into the future. The subtle difference is that the mean is calculated using past data. Key to understanding number 2. Exponential distributions can be used when events occur independently and at a constant average rate. If a random customer comes into our store at a given time, that event does not normally affect when another random customer comes in. The events occur independently. Now, a constant average rate is not the same as a constant rate. With a constant rate, there would be exactly one customer in every 15-minute period. With a constant average rate, the length of the periods could vary, but on average, there would be one customer in 15 minutes. A constant average rate is a consequence of a property called memorylessness. Something is memoryless when the past has no influence on the future. For example, coin flipping is memoryless. The fact that you flipped heads 10 times in a row does not change the fact that the next coin flip has a 50% chance of being a head or a tail. On the other hand, memorylessness is not, for example, a property of things that decline with age. The time to engine breakdown in a car is not the same for a new car as for one with 150,000 miles on it. Car problems do not occur at a constant average rate throughout the lifetime of a car. The exponential distribution works in memoryless situations. Key to understanding number 3 begins by stating that the exponential is a family of continuous distributions. Distributions can be classified as either discrete or continuous. Discrete distributions are like the Poisson distribution on the left. The data is usually count data, which consists of non-negative integers 0, 1, 2, etc. Graphs of discrete distributions have a discontinuous pattern formed by adjacent bars, with each bar representing an integer count. Continuous distributions, like the normal and the exponential, are pictured as smooth curves. The data can be any real number, so all points between integers are filled with data whose probabilities are reflected in the height of the curve above them. KTU number 3 goes on to say, an individual distribution within the exponential family can be specified by a single parameter, either the mean mu or the rate lambda. It takes 2 parameters to describe an individual distribution in other distribution families like the normal, the F, or the chi-square distributions. But the exponential can be described with just one parameter, the mean or the rate. Take your pick. If you know one, you know the other. Remember that the mean mu is 1 divided by the rate, lambda, or vice versa. Here we show 2 members of the exponential family of distributions, the one with a mean of 2 and the one with a mean of 8. You can see how the curve flattens out as the mean increases. KTU number 4 states, the probability curve, PDF, of an exponential distribution approaches 1 as x approaches 0, and it approaches 0 as x approaches infinity. The probability of any individual value on the x-axis is the height of the curve above it. These probabilities are calculated using the probability density function, or PDF, for the exponential distributions. Now, unless we're in a science fiction movie, time does not move backwards, so the exponential distribution does not extend into negative values for x, which is usually time. So the probability is 0 of x being less than 0. For x greater than 0, the probability of x is 1 over mu times e to the power of the quantity negative x divided by mu, where e is the exponential constant whose value is 2.718. And since 1 over the mean mu equals lambda, the rate, then the probability of x is lambda times e to the power of the quantity negative lambda times x. Key to understanding number 5. Now, a cumulative probability is the probability of a range of values. Alpha and p are examples of cumulative probabilities. They are calculated as areas under a probability curve. With the exponential distribution, however, we don't have to calculate an area under the curve. We can calculate it using the CDF, which is known as the cumulative distribution function or cumulative density function. The cumulative probability of all values less than x is e to the power of negative x divided by mu, or 1 minus e to the power of negative lambda times x. If we plug in x equals mu, we find that the cumulative probability of all values of x less than the mean is about 63%, and the cumulative probability of all values of x greater than the mean is about 37%. This is true for all exponential distributions. Back to our example at the beginning. We own a small shop and one new customer arrives on average about every 15 minutes. That is, mu equals 15. We would like to close up shop 10 minutes early today, so x equals 10. What is the probability that a new customer would arrive within the 10-minute interval between the time we left but before our normal closing time? That is, what is the cumulative probability of x being less than or equal to 10? We insert x equals 10 and mu equals 15 into the cumulative density function, and we get our answer, 51.3%. Okay, that includes our clarification of the concept of exponential distribution. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book if folks like you tell me that more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available unplanned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. Now, I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a Statistics Tip of the Week series, as well as occasional posts showing that you are not alone if you are confused by statistics. I'll also be posting on the Facebook page Statistics from A to Z and on Twitter as @StatsA to Z.